Well, so I think we're almost done with the particle swarm. We covered all this, and the remaining is just 2-3 slides. Probably we have the steps, all the steps we covered. We discussed all the steps, and probably this is the parameters. What are the key parameters of the particle swarm? Key parameters that you want to set at the beginning. What do you think? Number of particles, yes, this is the population size. You need to, at the beginning, you need to define at the beginning. What else? C1.
Vmax.
Vmax. Okay, Vmax, and Vmax is controlled by a number of intervals. N. Okay, so you set the N, and definitely you have the maximum and the minimum of each parameter. Optimize the parameters, and then you can find Vmax and V minimum equal to minus Vmax. So N, the number of intervals, and also C1, the importance of the personal best, and the C2, the importance of the neighborhood best or global best or social global. Vmax, limit on velocity, all these should be set at the beginning. The number of particles, you can have 10 to 50 are reported as usually sufficient. If your problem is not that big, if you have like 20 optimized parameters or so, you can use this range of population size. C1 and C2 are usually set equal to 2, C1 equal to C2 equal to 2. In some variants of particle swarm, they said that C1 plus C2 must be greater than 4, and they set it equal to 2.05. So this is using the constriction factor. But anyway, you can have the simplest ways to set C1 equal to C2 equal to 2. That means you have equal opportunity of the local and global best, global search. So usually C1 and C2, no good reason other than empiricism. And these are based on empirical trial or attempts. Vmax, if too low, if you increase the number of intervals, as you know, the Vmax equal to parameter Xmax minus X minimum, optimize the parameter over a number of intervals. So it is governed by number of intervals. If you make the Vmax very low, and the N is very high, that you divide here Xmax and X minimum, you have very high number of intervals, then you limit the change in the position of the particle. You limit it. So it becomes too slow. So movement of the particles will be very slow. But if it is too high, also will be too unstable. Yani you are flying here and there, jumping from here to there, and this will create some of the big variation. And if you plot, for example, this is the objective function J, and this is the iteration. If you plot here J versus a number of iteration, J of the best in each generation or in each iteration, you can see this is the best, and the best is very bad here, and then it improves, go up and down, and until you have, this is the, if you plot the best of each iteration. So you can have this up and down, so you can have such case. But if you plot generally, if you plot J of the best found so far, so in this case you have the objective function is decreasing with number of iteration. So if you have the Vmax is too high, then you can face such case, and the best of each iteration is going ups and downs, and then you are flying here and there in the search space. So these are the particle swarm parameters, and this is the computational flow chart. You start with initialization. You set a number of population. You also initialize the solutions, the positions. You initialize the velocities. You set the weighting factor. This is also one of the parameters here that should be listed here. This is not given here, but this is also another key parameters. The whole weight of 0, the initial weight. The initial weight. So you need the initial weight, and if you use طبعا maximum number of iteration also we need it. And if you use a weighting factor or weighting update as W of T equal to alpha of T minus of omega of W of T minus 1, in this case also you need to set the alpha very close to 1. Very close to 1. It looks like this slide is not complete. So we add here a weighting factor, the initial weight. You need to have the initial weight. If you use this rule to update the weights from iteration to another, in this case also you have to set alpha. If you use the other way, which is W of T equal to W of T minus 1 plus the initial weight minus the final weight over the maximum iteration.
Is it plus or?
That's minus, yes. It's minus. So this is minus. This is not plus. Then the weight is decreasing, right? The weight is decreasing. If each time طبعا this is the higher than this. So in this case, if you use this rule to update the weight at each iteration, so in this case you have to set the maximum number of iteration, and also you have to set the you have to set also the final value of the weight, W final. So you have to set also a W final in order to be able to calculate this. So you need to do this. And this is, it seems, the slide was not complete. So usually, as we mentioned before, in W of 0, we set it as 1.2 or 1.4, and within this, or 1, 1.2, 1.4. W final, this could be 0.4. طبعا number of iteration you can set it 100 or so, or 200 or 300. يعني. Okay. So these are the BSO parameters. We start with initializing the population, positions, velocity, weight, iteration counter, and so on.
Doctor.
Yes, please. Abdullah,
what is the typical value of the maximum velocity, Vmax?
Vmax is different from one direction to another. This is equal to x max minus x minimum over n, and it is governed by n. As we mentioned, you cannot say, we can say in the typical value of n. لأن الدايركشن أو الoptimized parameters are different in order. And for example, in our problem, when you have a controller, you need to design K with T1 with T2, a range of K from 1 to 100. So this is the minimum and this is the maximum. And T1 from 0.1 to 1 second. And the T2 from 0.01 to 0.1, for example. So the maximum and minimum are different from one direction to another, from one optimized parameter to another. So in this case, you need to fix this n. You say, no, I will divide the range of K over 10 intervals. So I put here 10 intervals, so I can limit. So in this case, the Vmax here is 10. If you divide this by 10, so it becomes 0.09 Vmax. If this is 0.09, if you divide it by 10, this is 0.009. This is Vmax in this direction. It's okay, Abdullah?
So my question now is what is a typical value of n?
N is, we can say it here, N usually you set it 8 to 10. Okay?
Okay.
You can set it 8. That means when you divide this range of these parameters over 8 intervals or 10 intervals. So this is the typical range of n.
Yes, now it is clear. Thank you.
As we mentioned, then if you reduce n more, if you make n equal to 2 مثلا, now n equal to 2, that means when you divide the interval to 2 intervals only, this range to 2 intervals. That means if k equal to 10 مثلا in one solution, this 10 can be go over the 50 or the half of the interval, half of the range, so it could be 60. So you jump from 10 to 60 right away. So this will give you, as we mentioned here, unstable performance here. But of course, if you make it very, very high, so you limit the variation of the position of the particle, so you will experience slow convergence. So you need to compromise. You need to compromise. This is a key parameter that you need to attempt 8, 9, 10, and then you can see which one gives you better results in terms of the solution quality, in terms of the iteration number or the computational time. And you can look at it at different aspects in here. Is it clear, ya Abdullah? Or you have another question?
Yes, that is clear. Yeah.
Okay. So lower your hand, please. So after initialization of the population and the velocity, position and the velocity, in this case, you can calculate the objective function for all the population, and then you can, for each particle, you set local best equal to the particle itself. And this is the initialization step. And also you can search for the global best. So you can search for the best solution with the minimum objective function, assuming that we are minimizing the objective function. So the global best can be set. So you have a local best here for each particle, and you have global best for all particles here, one solution, which is global best. So how many local best do we have in particle swarm? How many local best and how many global best?
We have n local bests.
Number of local bests equal to the number of particles, equal to the population size, the number of local bests. Of a number of global best?
It's only one.
It's only one solution. So you have here for each solution, you have its local best and you have global best here. So this is the initialization step, and then we will go to the loop here. So after doing this, we will go to update the particle velocity. We define here the local best and the global best, and the velocity is there, and weighting is there, and so on. So you can update the particle velocity in the three terms that we have. The first term depends on the earlier velocity. Second term depends on the difference between the current position and the particle best. And the third term is the social part of the particle swarm, which is the difference between global best and the current position. So you update the velocity, and then you update the position of the particle, and all the position plus the updated velocity. And then you calculate, you have new positions here. And if you have new position, you can go and calculate the objective functions. And then you update the local best for each particle. And each particle can compare the current position with the all the local best, and then can update the local best. And also, after calculating the objective function, you can get the minimum, and you can get the best solution, and you compare it with the best solution given here. And in this case, you can update the global best accordingly. And then you can see global best better than the best solution. And if you find here in the second or in the first iteration after the initialization that the global best you found here is better than the one stored before, or the one found so far. So if this is the case, let us see what if no, you proceed. But if yes, you need to update the global best. And we are keeping your mind and we are looking for the global best or the optimal solution. So if you found better solution, then you have to update this, update the best solution, and then continue. And then you check the stopping criteria. If you reach to a stopping criteria, of course, you can, if you want to expand this here, and I think we already covered it. If you go in this branch and you update the best solution, then you can set a counter here equal reset the counter kbest equal to 0. You can reset the counter. But if you don't, then you can add here kbest equal to kbest plus 1. Kbest plus 1. So then this will be used here for stopping criteria. As we mentioned earlier, stopping criteria, you can stop if you reach to the maximum iteration, but wisely you can stop if the best solution doesn't change for a long time. And you can say, and if kbest equal to 20, then I can stop. That means, the best solution doesn't change for 20 iterations. So I can stop here. And this is the objective function in this case. The objective function is reducing, and then it will keep constant here for 20 iteration. So I can stop here. So you can expand this. So the stopping criteria, if you met the stopping criteria, in this case, you can stop the search. Otherwise, you can go and update the iteration counter, iteration equal to iteration plus 1, and then you update also the weight, but whatever the rule you use here, you update the weight and you go back. When you update the weight, you go back to update the velocity again and again. So this is the flow chart of the procedure or of the BSO algorithm. Do you have any question? Okay, so this is the particle swarm. Yes, please. You have a question, Salim Ghanem. Salim, please.
Yes, Professor. So for stopping criteria, we always look at the global best in this case.
Yes. طبعا we are interested in global best. This is what we actually looking for. يعني احنا عاوزين ال outcome of the whole search is the best solution. We need the best solution. So this is the best solution at the initialization step. And once you have here, you found the solution after updating the position and the velocity and so on. If you found a solution which is better than the stored one, then you update the stored one. You update the best solution. Okay. Otherwise, you go forward and you do another iteration, and then you update, and then you go and so on until you meet one of the stopping criteria. Is it clear, Salim?
Yeah, Professor, clear.
Okay. Abdullah Yusuf?
What is the rule of the weight in particle swarm algorithm?
If you look, if you go back to the velocity update, Abdullah. Yes, here it is. Velocity update. How to update the velocity? Yes, here it is. This is the weight. This weight reflects the dependence of the new velocity to the old velocity. يعني we have an inertia. يعني انت لو انت يعني في inertia, if you are moving, So you have an inertia, right?
Yes.
So if this is the velocity, so you go with this velocity multiplied by W. So this is the first term of the updating the velocity. So you multiply the weight by the old velocity, and then you go in the direction of the vertical best, and also in the direction of the global best. So you have another component here for cognition part, which is parallel to the difference between x and the vertical best. So this component is parallel to the difference here, and another component parallel to the difference between the current position and the global position. So this is the third component of the velocity. So parallel here, so you have here the current position. So you add the previous position with the new velocity, and you end up with the new position here. This is the updated position. And okay, so this is the case.
So in the end, the weight after updating it will become 0, right?
The weight after
we update it several times, it will go to 0, isn't it?
It will reduce, as we mentioned, in W of t. I will weight W of t equal to alpha times W of t minus 1. So if you take this as 0.9, so and then the second iteration would be 0.81, it will be 0.72, will be 0.56. It will not be 0 at the end. يعني لأنك أنت you multiply by 0.99 يعني or 0.95 or 0.99 يعني it's very close to 1 but less than 1. So the weight here is reduced to very low value here. Okay, but it will not reach 0 يعني. Okay, so the other way is to have W of t equal to W of t minus 1 minus W of 0, the initial value 1.2 minus the final value 0.4 مثلا over number of iteration مثلا وليكن 100. So at each time you reduce, this is 0.8, 0.08, this is 0.8 over 100, so it becomes 0.008. So each time you start with 1.2, next iteration it will be 1.192 iteration and so on. So you are reducing it step by step up to 0.4, and you will reach to 0.4 at the end. And if you reach the maximum iteration, search will stop. And at this 100 iteration, W will be 0.4. Okay, so it will not reach 0 again. And in both ways, it will not reach 0.
Okay.
Yes, go
ahead. This answers my question. Thank you.
Okay, welcome. Well, so this is concludes the particle swarm. And we will start And I hope we can finish it today. And we need to move to another subject. Plus, now you already, I think we covered all the aspects of such techniques. We introduce here one of the algorithms which initiated by the physical process. Genetic algorithm and all these techniques have the particle swarm. It's bio-inspired, but here the stimulated annealing inspired by the physical annealing process. Annealing is a process, mechanical process or thermal process, and we simulate this physical process of annealing in order to solve the optimization problem. We will discuss the analogy between the annealing process and also the optimization technique here. So the annealing is you have a metal here, or and this metal you heat it up until melting point, and then you cool down this material in steps. You decrease the temperature in steps, and at each step you keep it until all the molecules or particles of this material to be arranged or to settle down, and then you decrease the temperature, and then you decrease the temperature, and then you decrease the temperature until you end up with the minimum energy stored here in the particles. So this is the annealing process overview. We will see and what is the annealing as a physical process, and how to make an analogy between the annealing, the physical process, and also the simulated annealing algorithm. And we will see the definitions and the components of simulated annealing, and we will see also in steps how it works and the key parameters of the simulated annealing. So annealing is a heat treatment that alters the physical and sometimes the chemical properties of a material to increase its ductility and to make it more workable. So you have it here. This is the material at the beginning. It's very hard, and when you annealed it, it becomes ductable and also more workable, more flexible. So the annealing is performed by heating the material. So this is the first stage. You heat the material up and then slowly letting it cool to room temperature. You decrease the temperature in steps until, of course, to the room temperature. So we have two stages here in the physical annealing, heating up and cooling down. So simulated annealing is an optimization technique that simulates the physical annealing process in the field of optimization, combinatorial optimization. Annealing is the physical process of heating up a solid until slow down, decreasing the temperature. This is already done. At each step, the temperature is maintained constant for a period of time sufficient for the solid to reach thermal equilibrium. And there is no change in the particles' energy. So you reach to the thermal equilibrium, and then you decrease, you cool it down to a certain temperature. Yani, for example, if you heat it up to, for example, 200 degrees centigrade, then we need to cool it down. But this cool down will be in steps. So, for example, 180 degrees, step 10, 160 degrees, 140 degrees, and you wait, and then you cool it down to 120 degrees and wait until you reach to the thermal equilibrium, or the molecules arrange themselves in a certain position. There is no other change. And then you reduce it to 100 degrees, and then you start decreasing it in steps. Okay, so in 1953, Metropolis and the others proposed the Monte Carlo method to simulate the process of reaching thermal equilibrium at fixed value of the temperature T. In this method, a randomly generated perturbation of the current configuration of the solid is applied so that a trial configuration is obtained. What we want to say here, how to simulate the thermal equilibrium. You have a current position. This is the current position. And you perturb this position. And if you move somehow in the neighborhood here, and you have here another solution, this is a solution, and you have another solution here. And if you have this energy of that solution is lower than this solution, that's fine, we can consider this. But if this is higher than this, and if you go to this way, another solution in the neighborhood of that solution, if you go in this direction, and you end up with all these are unacceptable solutions. So that means, this, solution is stable solution, or you reach to what we call the thermal equilibrium. There is no movement, which is better than what we have. So let EC, the energy of the configuration, current configuration, and ET is the energy of the trial configuration. This is the current configuration, and any one of those will be a trial configuration. Configuration represents a solution in optimization problem. I mean, this is the configuration here. So the energy level of the current and the trial configuration respectively, and the energy is similar to what we have in optimization. It's objective function. And E is similar to the objective function in optimization, as we will see in analogy in next slide probably. So if ET is less than EC, that means the trial configuration is better than, has lower energy than the current configuration. Then a lower energy level has been reached, and the trial configuration is accepted, and it becomes the current configuration. So we move from this one, this is position 1, and this is position 2, trial, in the neighborhood. We try in the neighborhood of the current. This is the current, and this is a trial position. If the energy of the trial position is lower than the current, that means when you reach to better solution, and you can consider, now you move from this position to that position, and this position now becomes the current position. And then we will see in the neighborhood of the current position, again we move in any direction here. So this is the solution. This becomes a current, and this is a trial. And we also check whether the energy of this position is better than this. So we accept it. Otherwise, we will not accept it, and we will keep this as a current configuration. So if ET is lower than EC, then the lower energy level has been reached, and the trial configuration is accepted, and becomes the current configuration. On the other hand, if ET is greater than EC, the trial configuration could be accepted with probability proportional to the e to the power minus delta E over the temperature T. So you can still, if the energy here is higher than this, the energy of this position, you can still, but with the probability is proportional to this value, as we will see later on in details. Do you have any question? The process continues until the thermal equilibrium is achieved after a large number of perturbations. Okay, so by gradually decreasing the temperature T and repeating the Metropolis simulation, new lower energy levels become achievable. And as T approaches 0, least energy configuration will have a positive probability of occurring. If you look at this, at higher temperature, let us see here, if T is very high, let us take T is an extreme case. If T is infinity, very high value. So what do you think this value would be? Becomes
1.
Becomes 1. If T is very low, let us say 0. So this E to the minus delta E over T becomes a
0.
Becomes 0. So if T becomes very small, when you cool it down, when you cool the metal or material down, so the probability of accepting the lower or the higher energy configuration becomes very, very low. And at the beginning, when T is very high, you can accept the high energy configuration. Keep in your mind then how we need to minimize. So higher energy معناها bad solution. Lower energy معناها good solution. So if T is very high, we can accept the higher energy configuration or bad solutions. But when we cool it down, when we reach to the very low temperature, in this case, the acceptance would be very, very limited here. And this is, if you still remember, the non-uniform mutation and genetic algorithm. Also, we said at the beginning we can accept, we can move very far from the solution, but at the end of the iteration or generation, it becomes very, very limited change. Analogy. At first, the analogy between the physical annealing process and optimization problem is based on the following. The solutions in an optimization problem are equivalent to the configurations. So the configuration is simply the solution. The cost or fitness or objective function of a solution is equivalent to the energy of the configuration. EC and ET, energy of the current or energy of the trial configuration, as we mentioned earlier. In addition, a control parameter, we call it CB, control parameter, is introduced to play the same role as temperature. At temperature, we will cool down, we will decrease the temperature, and also we will decrease this control parameter with iterations. Okay, so this is the analogy between the simulated annealing and the physical annealing. Definitions. So here in the simulated annealing algorithm, we will use the current solution. We will use also the trial solution, and we have best solution. طبعا you have X current, X trial, and X best. طبعا X current هو solution. The X current is a vector, real valued vectors with m optimized parameters, or has m dimension, and this m is the number of optimized parameters, similar to particle, similar to the chromosome. So the solution here is similar format. So we have X current, we have X trial, and we have X best. And these are solutions of the problem. The trial solution is created. How to create the trial solution? And we assume that when we start with the current, we are at a certain configuration. We have a current solution. How to generate the X trial? How to generate the trial solution in the neighborhood of the current solution? And we will not go far from the current solution, but the trial solution is created in the neighborhood of the current solution. Of course, as we have in the particle swarm, we have intervals. We define V also, V max. When we get the V max, we divide the intervals in order to define the neighborhood here. So you can do the same for the simulated annealing to define the neighborhood. If this is 0 to 100, and you divide this to 10 intervals. So in this case, the radius of the neighborhood is 10. You can go here minus 10, or you can go here plus 10. So the neighborhood, the radius of the neighborhood is plus minus 10. So this is the neighborhood definition is limited by a radius characterized by the range of the kth optimized parameter and given by the radius, or the distance, the maximum distance that you can go over it in any dimension. And we have different dimensions, as we just pointed out, for K and T1 and T2, we have different radius, or we have radius for each dimension. So you can have the radius in K dimension, in T1, in T2. You can set the number of intervals here. Again, you can have it 8, 10, 12. Of course, you can have 9 and 11 and so on. So you can define the radius of the neighborhood in each dimension, similar to Vmax in particle swarm. So this is the neighborhood. So for example, if you have X current equal to 30, 0.9 and 0.2. This is X current. And you know the bounds there for K ranges between 0 to 100 or 1 طبعا. 0 معناه ان there is no control to 100 T1 from 0.1 to 1 second and T2 from 0.01 to 0.2 second. So this is the range of the optimized parameters. So if you select, for example, n equal to 10, select n equal to 10. We need 10 intervals here. So D in the dimension of K, D max equal to 100 almost over 10, so 10. D in the dimension of T1 will be like 0.9, 0.09. And the DT2 max will be 0.009. Okay, so this is the neighborhood, this is the definition of the neighborhood. And this will not change, definitely. And you can have this radius at the beginning of the code, and a number of intervals you set it, and then maximum and minimum are constants. They are not changing, but this is the definition of the neighborhood. So for this current position, if you want to create a trial solution, what you will do? This is trial solution. How to create it? Can we do it similar to particle swarm? It's a similar concept. It's nothing new. And we have the velocity of the particle swarm. And we have plus minus V max. We have here plus minus D max. So if this is the current position, so we can go up to 40 or we can go up to 20. So if you want to disturb this, you can create a random number, and then you have here 30 to 30 plus any random number between plus minus 10. You can have here any random number between plus minus 10. So you can say minus D max, and here D minimum, plus R times D max minus D minimum. And this is the random number between 0 and 1. So if it is 0, for example, if it is 0, then this will eliminate, and you have 30 minus 10, so it becomes 20. If R equal to 1, so this is minus D max, and we have here D max. If this is 1, so this is D minimum here. You have D minimum is minus D max. Keep in your mind, this is minus D max. So minus D max was D max, and we have here minus D max. It becomes D max, which is 10. If a 10 plus 30, it goes to 40. So you can disturb this current configuration, current solution, to create a trial solution in such, in such a way. So you can have generate here like 35. This is a trial solution, and this is around 0.9 here, within the bounds of 0.09 to minus 0.09. So we can have here 0.95, and this one could be from 0.2. We can have plus minus 0.09. So this could be 0.1. 0.195 مثلا. And this is a trial solution created from this current solution in the neighborhood of the current solution. Is it clear? Is it clear? If you have any question, don't hesitate. We need to explain as we are going on.
Yes, clear.
Okay, great. So n the chosen number of intervals and the clear dimension. Then the trial solution is created as follows. X trial equal to X current plus the distance that you will move here. We move here 5, we move with 0.05, or minus 0.05, 0.05 here. So this is D, and D is created between minus D max to D max. This is the case. Okay. So and the dj equal to 2r minus 1 times d max. Well, similar to this. Yani this is 2r minus 1 times d max. هي نفس الفاليو. If r equal to 0, then we have minus d max. If r equal to 1, then we have d max. If r 0.5 مثلا, for example, then becomes this is 0. يبقى الترايل solution هو نفسه الكرنت solution. In this dimension, طبعا at each dimension you create another random number. So with this rule you can create the X trial in the neighborhood of X current. Now we need to, in the physical annealing, we are increasing the temperature at the beginning. This is the heating up process or heating up stage. Up to which temperature we can go up? And you are heating up until the melting point. And how to simulate the melting point here? And till which temperature we can stay? We need now to move with the cooling down stage. At which temperature we need here? We can reach to this temperature by defining what is the acceptance criteria. Acceptance criteria, at any iteration, the trial solution can be accepted as the current solution if it meets one of the following criteria. As we mentioned, in any current position, we will create a trial solution. So this is X trial and this is X current. If the objective function of Jt less than Jc, so we will accept it right away. This position is better than this position, assuming طبعا the minimization problem. But now if Jt is greater than Jc, if the objective here is worse than the objective here, so this is the bad solution or worse solution than this one. So in this case, we will not eliminate the trial solution. We will consider it, but under a certain condition. So we will, if J of xt is less than J of xc, or second condition here is if J of xt is greater than and e to the power minus delta E over the temperature is greater than or equal a random number between 0 and 1. So you calculate this, you have J of xt and J of xc. So this is positive, and this amount now, we will not go to this rule until we have J of xt is greater than J of xc. So this is positive quantity. So e to the minus delta J over the control parameter or the temperature is greater than a random number between 0 and 1. So again, if you have a CB very high, if CB is very high, so this is equal to 0 and this goes to 1. So 1, definitely 1 is greater than or equal any random number between 0 and 1. So with very high temperature, we can accept the trial solution even if it is a bad solution. But when we cooling down, when we start cooling down and CB approaches 0, in this case, if this is 0, and in this case, this becomes minus infinity, so this becomes 0. And 0 is not greater than or random number. So in this case, we will not accept, when we're cooling down, when we reach to the final stages of the simulation, we will not accept any trial solution if it is worse than the current solution. Okay, so we can accept the trial solution if one of these conditions has been satisfied. Okay, so as you can see here, CB plays a great role here. The temperature plays a great role of the acceptance of the solution or rejection of the solution. So which temperature we will say now we can start cooling down? Which CB value? How much is CB in order to say okay, خلاص, we will stop heating up, we reach to the temperature level that almost any trial solution will be accepted if CB is very high or temperature is very high. So we need to find out at which temperature or what is the value of CB that simulate the melting point of the material, and then we can start cooling down. So this will be governed by what we call the acceptance criteria. Acceptance criteria. So the random number between 0 and 1, okay. And J of xt and the J of xc are the objective function associated with xt and xc respectively. Everything is clear here. So criteria B indicates that the trial solution is not necessarily rejected if its objective is not as good as that of the current solution, with hoping that a much better solution becomes reachable. For example, if you have this kind of objective function that we need to minimize, that we need to search for the local or the optimal solution, which is here. For example, if you have a current solution here and you move a current solution, you go in the neighborhood, you reach to this one. This is the current solution, XC, and you reach to XT. Definitely XT will be accepted. If you go here, still the XT will be accepted. And if you go here, you can accept still, here, this solution is worse than this solution. Am I right? You can still accept it. Hopefully, you can throw the neighborhood of this one. You can, do some, hill climbing, and then you can reach to the optimal solution later on. So you will not reject this solution. If you reject it, you will be trapped in this local optima. But if you accept it, this could lead you to a better solution or better search area. So hoping you can reach. So the acceptance ratio can be defined as such. At a given value of the CB, you can create, in order to check the melting point, you can create 100 solutions, trial solutions, 100 trial solutions. You have a current solution, and you can generate 100 trial solutions in the neighborhood of this one. This is the current, and this is the neighborhood, and this is the have movement. طبعا مش لازم يوصل للend of the radius, but you can of course have solutions here. So you generate 100 solutions around the current solution. Okay, and then you can see how many of these solutions will be accepted. N1 is a trial solutions can be randomly generated based on the acceptance criteria, and N2 of these solutions can be accepted. And you check the acceptance criteria that we have it here, these acceptance criteria, and you can count how many solutions will be accepted. How many solutions will be accepted, and you can have the acceptance ratio is defined as N2, the accepted number of accepted solutions, over the number of trial solutions generated. So if you have this ratio very close to 1, and you generate 100 solutions, trial solutions, and you accept 100 trial solution, معناها انك انت you reach to the melting point. The CB becomes very high. Fawzan, do you have a question, Fawzan?
Yes, quickly, بس على conditional criteria before. Now we said that when we select randomly, in quality here, should we keep it like greater than or equal? For example, if we have like 0, if we reach like a CB to be 0.
CB?
Yes.
Okay.
Then we will have like there is a possibility that we have like a 0 greater than or equal to 0. So should we consider it like equal, greater than or equal?
Probability كام؟ يعني هو first الCB will not equal to 0. يعني أنا بناخد الاكستريم كيس just to explain the concept here. يعني.
Yes.
The CB will not reach to 0. Okay, it will be very low, but will not very low compared to the initial value. Okay, and you start here with very high value, very high temperature, very high control parameter, and you start cooling down. CB will not reach 0, and even if it is 0, يعني to have a random number equal to 0, يعني ده انت تبقى محظوظ قوي يعني.
لا so just to make sure يعني إنه should we neglect it or not? That's not
يعني almost يعني this will يعني very rare to happen يعني. But again, CB will not reach 0 يعني.
Okay, clear.
So with this acceptance criteria, you can count how many solutions will be accepted. And if this acceptance ratio is very high, is almost 1, in this case, that means when you reach to you heat it up until you reach to the melting point. Very high temperature. لأنه acceptance ratio at very high temperature will be almost 1. So what you can do, لأنه one of the key parameters here is the CB. What is the CB0? From where we can start cooling. So what you can do is following. You can start with any value of the CB. CB here equal to 0.1, for example, or 1. Let us start with 1. But 1 is, we don't know 1 is very high or very low. We can start with very small value, 0.01. And then this is a heating up. So you increase the temperature. You accept with this value of the CB, you accept you do 100 trial solutions and you see how many accepted solutions you calculate this. If it is gives you مثلا 0.1, now very far from 1. So let us heat it up again. We increase this CB to, for example, 0.1. We multiply by مثلا a factor which is 1.5 مثلا. So this becomes 1.015. And then at this level of CB, we can create 100 iteration, 100 trial solution, and we see how many accepted at this value of the CB. If it still below 1, then we can heat up again, and we can heat up, and we increase the temperature. We increase the CB by step until we have the acceptance ratio approximately equal to 1. In this case, we can stop the heating up process and we start the cooling down process. So this is the usage of the acceptance ratio here in the solution, in the algorithm. And then you have cooling down. You can cool down the control parameter or the temperature. Specifies a set of parameters that govern the convergence of the cooling schedule. This set includes an initial value of the control parameter. The initial value of the control parameter هي الفاليو اللي هنا اللي هي at the melting point. So this is CB0 and you CB final here. And you cool it down in steps. So a decrement function for decreasing the value of CB. And this is again similar to what we have in particle swarm. You have in particle swarm, you have the weight of T, and you know how to reduce this weight of T at each iteration. You can have it equal to alpha W of T minus 1, or you have it W of T minus 1 minus this bar. So you can do the same for the CB. CB in cooling process, you reduce CB. You can define CB initial, this value, and the CB final and number of iteration, and then you can decrease the CB at each time, or you can use this also decreasing schedule here. So you can define alpha equal to 0.99, and then you can decrease CB equal to 0.99 CB. And here, this is of course in coding. You can do this. CB equal to 0.99 times CB. So at each iteration, you update the control parameter. So CB0, decrement function decreasing to CB, and a finite number of iterations or transition at each CB level. Okay, for this. So what you will do here, actually, as we mentioned, at this level, you have a current solution and you move to the trial solution. You may accept it, and then you move to another trial solution. You do some iterations here until you found that the current solution doesn't change for a long time. If the current solution doesn't change for a long time, then you reach to the thermal equilibrium at this level, and then you start cooling down the CB by multiplying it by 0.99. So you go to another CB value, and at this CB value, you have the current solution, you create trial solutions. You have, for example, you do and you accept, you reject, accept, reject. If the current solution at this level doesn't change for a long time, then that means when you reach to the thermal equilibrium at this level, and then you multiply, you go to cool down again, and so on. I hope things are clear. The initial value of CB should be large enough to allow virtually all transitions to be accepted. And as you mentioned, the null acceptance ratio should be almost equal to 1, and then we can start cooling. However, this can be achieved, the cooling down achieved by starting off the small value of the CB0. And okay, so this is the heating up process. We start with a very small value of CB, and we multiply by alpha, but this alpha is not of the alpha of the particle swarm. Alpha here is greater than 1. So you start with very small value, and then you heat up, you multiply by alpha, you heat up, and so on until you reach to this level, and then you start cooling down. So this is simulate the heating up process. You multiply CB0 by alpha, alpha is greater than 1. And then the process continues until the acceptance ratio is close to 1. And then you start heating up process in physical. So this is equivalent to the heating up. And the decrement function, now we start cooling. CB is given by CB equal to mu times CB, where mu is less than 1. So you start decreasing the CB, and where mu is a constant smaller, but close to 1 typical value between 0.8 and 0.99. So it's a little bit confusing with particle swarm, but this alpha in particle swarm is less than 0. This is a heating up, and this is a cooling down, so mu should be less than 1. Do you have any question? Type. It occurs when thermal equilibrium or equilibrium condition. It occurs when the current solution doesn't change for a certain number of iterations at a given value of CB. As you mentioned, we do cooling in steps. This is CB0. We multiply it by CB equal to mu times CB. So at this level, you have current solution, and then you try the trial solution, you accept it, or you go here and there, you create trial, you may accept it, you go back to current, and then you create another trial. If the current solution doesn't change for a long time, that means when you reach to the thermal equilibrium at this level of the temperature. So once you reach to this thermal equilibrium, you cool down again, you reach to another CB equal to mu CB, and then you with the current solution you do some trial solutions, and then you cool down, and with this level you have some surge here and there. So this is the situation. The stopping criteria is similar to the what we have in particle swarm. If of this number of levels, the current solution doesn't change, or the best solution you have doesn't change for a long time of these steps of cooling steps, these levels. We have here two stopping criteria, by the way. One with at each level you have a stopping criteria, And based on this stopping criteria, you cool down to another level of CB. What we mean here by the stopping criteria of the technique, the whole technique, and we have, for example, 10 levels of CB without the changing of the best solution. So we can stop the search. There is no need to cool it down again and again. So we have here stopping criteria. The search will terminate if one of the following criteria is satisfied. A number of Markov chains. These are called Markov chains. Markov chains. This is the Markov chain. This is the Markov chain, and so on. This iterations, since the last change of the best solution is greater than a specified number, and the number of Markov changes reaches the maximum allowable. So number of iterations or number of chains, and number of steps here to cooling down, you specify it at the beginning. You will cool down over 100 iterations, and then if you reach it, then you can stop the search. Okay, I think time is over. انتوا شباب معايا ولا انتوا مشيتوا من 9:30 ل 5 احنا عدينا التايم without any further notification.
I think with the examples it will be more interactive.
Yeah, of course, definitely. Yes.
Because in previous using the example and discussing and
yeah, inshallah we will explain it later when we say when we go to the algorithm itself, the step by step how to implement it.
inshallah.
So do you have any question? If you have any question, please ask. If you don't have, then you can leave.